So today we're going to start a new section. We finished off last week with accelerating fluids, and we did linear acceleration and rotational acceleration. This week we're going to look at flow visualization and kinematics of flow or dynamics of flow along a streamline. So if we want to talk about fluid flow, we have to basically understand that there are many different types of flow. So first of all is unsteady or steady versus unsteady flow. We have uniform and non-uniform flow. There's viscous and inviscid flow. Inviscid flow is essentially flow where viscosity is neglected or negligent, or the effects of viscosity are so small we can call it inviscid. There's laminar and turbulent flow. There's external and internal flow. There's compressible and incompressible flow. And there's 1, 2, and 3-dimensional, or just called multi-dimensional flow. So we'll go through each of these individually, but these are some of the basic distinctions and different types of flow. And flow can have multiple of these. We can have inviscid laminar flow. We can have steady external laminar compressible flow, and so on. But for each one of these conditions, we typically have flow is one or the other. It's steady or unsteady, uniform or non-uniform, and so on. So what is steady and unsteady flow? Well, just to kind of show a diagram here, steady flow is essentially flow or any flow condition does not vary with time. So flow conditions could be pressure, velocity, density, temperature. These are all constants. They're not changing with time. So we can write steady flow is the case where we have our flow condition, which could be our pressure, velocity, density, temperature, do not vary with time. So if we were to write that in an equation, we could write the derivative of our velocity with respect to time would be equal to the derivative of our density with respect to time, equal to the derivative of pressure with respect to time, equal to the derivative of temperature with respect to time. They're all equal to 0. So steady, as it indicates, just means that it's in a steady state. Things aren't changing over a period of time. So here is just an example of a steady flow, for example, could be flow through a pipe, and at any given point along that pipe, our pressure is constant, our velocity, our flow velocity is constant. In the middle, we have quasi-steady flow, where we have maybe some fluctuations due to a geometry change or some feature in our pipe that's causing the flow to change. But even though it might be somewhat unsteady, some distance away from that on either side, the flow conditions could still be steady. Unsteady flow could be something like draining a reservoir, where the pressure due to the height of that fluid is changing because as it drains, that amount of fluid is decreasing. So our pressure, therefore our velocity, and if it's compressible, maybe our density is changing all with time. So that would be, again, a good example of unsteady flow. So we can write unsteady flow would just be our flow conditions are changing with time. So many devices such as turbines, compressors, boilers, condensers, and heat exchangers operate for long periods of time under the same conditions, and these would be classified as steady flow devices. So again, turbines, compressors, boilers, condensers, heat exchangers, something that might be running at a relatively constant rate or constant operation for a long period of time can be considered a steady flow device. uniform and non-uniform flow. So uniform and non-uniform flow can kind of be easier to visualize if we also pair it with steady and unsteady flow. So in uniform flow, all fluid properties such as the velocity, pressure, temperature, etc., do not vary with position. The flow is just downstream of a well-rounded pipe entrance, for example, is nearly uniform, except for a very thin boundary layer at the wall, which we're going to see more about later. But flow in ducts and pipes and at inlets and outlets tend to be uniform flow. Non-uniform flow, the simple definition would be like when flow is not uniform, but it's when our flow changes with position. So if we imagine this here, a stream or a river, uniform flow would be if we took a cross section of that river, as shown here, we can see all of these, you zoom in a little bit, all of these vectors for the velocity of the flow or the flow rate of the river is the same. Anywhere in that cross section, our flow rate is the same. At the bottom, we have non-uniform flow. So we maybe have our water at the surface is flowing faster than the water that is at the bottom of the river and the sides of the river. So depending on where we are in that cross section, our flow is changing. And then we compare this with unsteady flow. So we have unsteady uniform flow in a given cross section. Maybe the velocity is increasing or decreasing. It's changing with respect to time. And then unsteady non-uniform flow, think of maybe rolling rapids where we have different flow depending on where we are in that cross section, and it's changing with respect to time. So we can say uniform flow, all fluid properties do not vary with position. So fluid properties do not vary with position. We tend to say, like I said before, that the flow in ducts and pipes and at inlets and outlets, we call those more or less uniform flow. So the opposite, non-uniform flow, is flow that is changing with respect to position. So next would be viscous versus inviscid flow. And we sometimes like differentiate between a viscous region and an inviscid region of flow. So viscous flow is a flow in which the frictional effects are significant, and they tend to be around regions close to solid surfaces. So inviscid flow is a flow in which the viscous forces are negligible, or regions that are far away from solid surfaces. And they could be found usually regions that are not close. I won't say far away, I'll just say not close to a solid surface. And I'll also say that if we think of what gives rise to viscous forces is a velocity gradient. So if we look at this example over here, we have airflow over an airfoil, and we can see the shaded blue region would be the region where we would have viscous effects that would dominate the flow. So that would be a viscous flow region. And at the edge of that viscous flow region, eventually our velocity gradient just becomes zero. Our velocity isn't changing as we move further away anymore. So at that point, we have uniform flow. Our velocity isn't really changing with position. And because the velocity of each air particle isn't moving relative to each other, there's no frictional forces. So that region outside of our boundary layer would be an inviscid type flow. So what here we could say is inviscid. And in here, viscous. So for inviscid flow, I'll just write a third point, tends to find out when we have uniform flow. and then viscous would be non-uniform. So next up is laminar versus turbulent flow. These are two very highly talked about. You've probably heard about these before this course even, the difference between laminar and turbulent. So the definition here, laminar flow is highly ordered and very organized flow in which fluid layers shear on each other. And highly viscous fluids such as oils flow in small pipes or narrow passages are typically considered or most often laminar type of flows. So laminar is highly ordered and very organized, and the fluid layers shear on each other. So examples of laminar flow would just be highly viscous fluids flowing in small pipes, for example. Think of pouring honey. So on the other hand, we have turbulent flow. Turbulent flow is defined as random fluctuations in velocity and highly disordered motion, so it's not organized at all. And examples of this could be the flow of low viscosity fluids such as air at high velocities, and this is typically turbulent flow. So turbulent on the other side is random fluctuations in velocity. It's highly disordered, and it's typical in low viscosity, high velocity fluids. So this is just showing above, this is just a faucet, and we have water. So in both cases, same viscosity, but at a low flow rate. We have laminar flow from the faucet. And on the right, we have turbulent flow, which is a higher flow rate. So we typically talk about a transition for a going from laminar to turbulent flow. If this is the same faucet and water going slowly out of the faucet, low flow rate can be laminar, and at a high flow rate is turbulent, there must be some point where we increase the flow rate and we get a transition from this low to high. So transition, we could define as the flow fluctuates between laminar and turbulent flows at some transition point. And the transition from laminar to turbulent flow depends on the geometry, the surface roughness, the flow velocity, surface temperature, and the type of fluid. So we'll just call the transition, at the transition point, the flow is fluctuating back and forth between laminar and turbulent flow. So let's look at this in a picture. So here's an example of the flow of smoke, and it's the warmer air stream, so it is rising in whatever fluid it is in. And as the velocity is increasing, as it gets further away from its origin, it turns from laminar flow, and at some transition point, it turns into turbulent flow, which looks like this disordered, chaotic region. So the transition from laminar to turbulent flow depends on the geometry, surface roughness, flow velocity, surface temperature, and the type of fluid. So the flow regime depends mainly on the ratio of internal forces to viscous forces. And the ratio of the internal forces to viscous forces is something we call the Reynolds number. So let's write flow regime depends on ratio of inertial forces to viscous forces. And we call this ratio Reynolds number. And we can express this Reynolds number, this ratio, in terms of some flow properties. So our Reynolds number, which is RE, see if I can draw a good R, is equal to the density of the fluid times the velocity of fluid times some characteristic length divided by mu. Or we could also write this as velocity times diameter of a pipe for pipe flow times nu. So in this case, our velocity, V, is our characteristic flow velocity. D is our characteristic flow dimension. Mu is our dynamic viscosity. And nu is our kinematic viscosity. Kinematic viscosity is just equal to our dynamic viscosity divided by our density. So if we just replace here our dynamic viscosity, mu divided by density, is equal to our kinematic viscosity, so it just moves over here. But just for reference, according to our textbook, the transition from laminar to turbulent flow happens when Reynolds number is around 2000. So if it's above 2000, Reynolds number is above 2000, we have increased velocity, say. So our V is increased, so our Reynolds number increases. That would be turbulent flow. And if it's below 2000, we have low velocity or a high viscosity in our fluid, then we would have more laminar flow. All right, so internal and external flow. I just drew some, or brought some, I didn't draw these, but here's some pictures of some examples where we might have internal versus external flow considerations. So if we think of a turboprop or a prop plane, these props are external. They're not encased inside some channel or a pipe or a duct. So that flow around those blades would be classified as an external flow. So external flow is the flow of an unbounded fluid over a surface. Internal flow is the flow in a pipe or a duct, and the fluid is bounded by solid surfaces. So it's not, I guess, unbounded flow anymore. There is some boundary. So if we think of a turbofan, the air that is flowing through the outside or these internal channels inside these ducts would be examples of internal flow, whereas the flow passing over a prop over here is unbounded. There's no container restricting the flow, so that would be external flow. So quite simply, we'll just call internal flow is the flow, internal flow, the flow in a pipe or duct if the fluid is bounded by solid surfaces. And then external flow would be the flow of an unbounded fluid over a surface. Next, we had compressible and incompressible flow. Now that's kind of difficult to visualize, but there's a technique for photographing shock waves from aircraft, and this is called a Schlieren image. And it is a picture of a US Air Force test pilot and his aircraft flying at supersonic speeds. And how this works is it takes the refractive index of the air, which changes depending on the density of the air, and it turns that into a photograph. So we can actually see the lines where we have different fluid densities. So we can visually see where this flow is incompressible, where the flow is compressible and the sort of degree of compression or change in density of the fluid as it's flowing. So this is kind of neat. We can actually see the shock wave front. So this is that's just a band of highly compressed air at that shock wave front. So if we think of moving through air, which is a gas, at a high velocity, that tends to be compressible flow. So compressible flow, we'll call this region over here. So this is the Mach number in different flow regimes. The Mach number is the velocity of the flow divided by the velocity or the speed of sound in that medium. So if a Mach number is 1, that means the flow is at the speed of sound. So anything above 0.3 of the Mach number or 0.3 of the speed of sound in the flow of a gas is compressible flow. So compressible flow is just very simply if the density of the fluid changes. And this is possible in fluids that are gases and generally when they're at high speeds. So the opposite of compressible flow would be incompressible flow. So incompressible flow, we said, is if the density of the fluid flowing remains nearly constant throughout. So densities of liquids are generally constant, and even at high velocities, the density does not really change, and it takes a huge amount of pressure to change the density of the fluid. So typically we say the flows of liquids are incompressible. So generally, liquid flow is incompressible. And if we have gases moving at low speeds, we can also consider those as incompressible because their density might be nearly constant throughout. So this example here is just for air. So yeah, hopefully to answer your question, Adam, is compressible flow possible with liquids? For any practical application, no, when we're just dealing with flow. If we're dealing with other properties of fluid, maybe we're sending shock waves or ultrasound, maybe we wouldn't consider the compressibility in that case, but for the realm of material in this course, we'll generally consider that liquids are incompressible, or the liquid flow is incompressible. So lastly, we have one dimension or multi-dimensional flow. So a flow field is best characterized by its velocity distribution. And if the velocity distribution is one-dimensional flow, that means the flow velocity only varies in one dimension. So in this example, 1D flow, our flow velocity varies in one dimension only. So in two-dimensional flow, you can imagine that the flow velocity would vary in 2 dimensions. And then finally in 3D flow, we would have the velocity varies in 3 dimensions. So a typical fluid flow involves 3-dimensional geometry, and the velocity may vary in all 3 dimensions. But sometimes we can simplify this down to fewer dimensions. For example, this airfoil section is 3-dimensional, but we really care about the flow in a certain plane. So we would simplify that down to 2-dimensional flow. And if we can prove that the amount of fluid flowing in and out of that plane is relatively insignificant, then we can validate an assumption that maybe a 3-dimensional flow could be modeled as a 2-dimensional flow. And then likewise, 2-dimensional flow, for example, flow in this duct at the top going through a venturi. Even though the velocity is changing slightly in that vertical direction, as it's shown there, it's not very significant relative to the flow in the x direction. So we can model most of this flow as just one-dimensional flow. So let's look at an example now where we have the development of the velocity profile in a circular pipe. So the flow is two-dimensional at the entrance region, where the velocity is a function of r and z. So r is just the radial distance from the center line of that pipe, and z is the distance along that pipe. So flow is 2D in the entrance. So that means our velocity field is a function of r and z. And then further downstream, the flow becomes one-dimensional, and the velocity profile fully develops and remains unchanged in the flow direction. So downstream, our flow fully develops and then remains unchanged in z. So our velocity field now just becomes a function of our radius r. So it's one dimension. So if we think about this, our flow velocity, our flow field, our function at each snapshot in, I guess I wrote z, but it shows x here. Let me just change that to x. So as we move further and further down our pipe, we enter the region which is the hydrodynamic entrance region, where our flow is two-dimensional because it's changing as we move further down that pipe. So that's the second dimension. The flow will be changing depending on how far we are from the center of the pipe. So that's our first dimension, our radial dimension. And then as we develop our flow in that x direction, our flow also changes. After a while, we get to a point which is called our fully developed, or hydrodynamically fully developed region, where we have fully developed flow. And this would be our fully developed region. So a lot of times when we do our analysis of fluid flow, we have to assume for our one-dimensional equations that we have fully developed flow. So we have doing our analysis at a section of pipe that is beyond any geometric change that is going to require a boundary layer forming, such as an entrance or maybe a device in the way that's disturbing the flow. So fully developed flow, we say this just means that we have one-dimensional flow in a pipe, and it's not changing the flow at one section of the pipe as long as the diameter stays the same, is not changing. So next things we have to visualize all these different types of flow is flow patterns and flow visualization. And there's three main flow patterns that we can use regularly, or we do use regularly, to understand fluid flow, to try and get information of what kind of flow we have with our fluid, so that we can either control it or model it or improve it or design bodies to flow through it faster, better, easier, whatever. So the three types of flow patterns are a streamline, path line, and a streak line. So for each of these pictures, let's say the top right Red Bull car with these paint lines on them, what kind of flow pattern do you think that would represent? A streamline, a path line, or a streak line? Do we have any ideas? Streamline until it reaches the red. No idea. Well, we'll get back to this and we'll figure out what our answer is once we define these. What about the one on the bottom? So we have some points for streamline and path line on the top one. And the bottom, this is a CFD simulation of a Formula One car and fluid flow over the aerodynamic components. So what kind of lines do you think they're visualizing there? Streak lines, streak line, since it leaves a flow trail. Well, for the bottom one, we probably can't really be too certain, but it might look like it's either a streamline or a path line. And then I would say the top one probably looks the closest to a streak line. So let's define sort of what these are. So let's look at streamlines first. A streamline is a line where any point along that line, a fluid particle's velocity is tangent to that line. So if we see here, this is a fluid particle's velocity at any point. So we could draw a particle here, particle here, particle here, so on. So imagine at the head of each of those arrows is our fluid particle, and the velocity of that fluid particle is tangent to the streamline at any point along that streamline. So velocity of fluid particle is tangent to the streamline. If that's true, then we think about the properties of fluids. They can't have two particles of a fluid to occupy the same space at the same time. So these streamlines can never cross. So there's a unique velocity at every single point in space. So streamlines do not cross. So that means that there's a unique velocity at every point in space. And our streamlines could also vary with time. So if we have unsteady flow, that means our flow is changing with respect to time. Our streamlines will also change with respect to time, and they will always maintain that first rule where the velocity of a fluid particle is always tangent to the streamline. So a stream tube is maybe a special feature or an arrangement of streamlines. And a stream tube is such that we have a bundle of streamlines that surround a region of flow, and the flow contained within that conduit, we'll call that tube, might be useful in some problems, but there's no flow across that tube. So it kind of isolates the flow inside and outside of that tube because those streamlines cannot cross. So a stream tube we'll call a bundle of streamlines that surround a region of flow. And the fluid flow, as it is contained in a conduit, is useful for some problems. And in 2D, a stream tube is formed by two streamlines. So in 2D, a stream tube is formed by two streamlines. So if we look at the figure on the left-hand side, we can imagine each of those streamline pairs could be a two-dimensional stream tube where the flow in between those streamlines is isolated from the flow outside those streamlines, and that's just because the streamlines are never going to cross. So the fluid is never crossing a streamline. So how do we model streamlines, or how do we describe them mathematically? So on the right-hand side here is just a diagram of a velocity vector. Let's assume that's just acting at some point in space, x, y, z. So on the streamline, during a small time, which we'll call small time dt, the fluid particle travels in 3 dimensions as much as dx, dy, and dz. So it might travel a little bit in the x direction, a little bit in the y direction, and a little bit in the z direction. So if our velocity vector v is equal to some function, or has its components, u, v, and w, and we can write u is just equal to the x velocity dx dt, v is equal to the y velocity dy dt, and z is equal to the z component of velocity, dz dt. And along a streamline, using the definition that the velocity at any point has to be tangent to the streamline, we can get the equation, a relationship for a streamline in 3 dimensions is dx over u is equal to dy over v is equal to dz over w or dr over v. So this would be 2 dimensions or 3 dimensions. And then if we had a 2-dimensional problem, we only have x, y, u, and v. So we can write dy dx is equal to v over u or dx dy. So all this is a starting point, an equation that represents the equations of a streamline. So if we have a flow field that's known, we can calculate the equation for the streamline through that flow field if we know our velocity through space. Shouldn't it be w is equal to, yes. Yes, it should. So that is a streamline. So now what is a path line? A path line is a little bit simpler, but it's if we were to just track a particle's path through time, the line that it would trace out for one individual particle would be called the path line. So if we had our particle, it's sitting here, and that's at time t0. And then after some amount of time, it's moved over here, and it's followed this path. And that could be t1, and then maybe sometime later, t2, and so on. So the path line is just the actual path that the particle travels over some period of time. So it's the actual path the particle travels over some period in time. This can be obtained experimentally. So a particle can be released within a flow stream, and maybe we can take a exposed photograph to collect in an image of that particle flowing through. If you think about this, if you ever done like a rubber ducky race down a river, if you were to trace the path of each of those little rubber ducks, that would be the path lines of the surface fluid flow of the stream that those little rubber ducks are racing on. So that would be a path line. And it can also be used to determine the average velocity on the surface of a fluid. So that is, if we know the position of a particle at some point in time, and we know the position of the particle sometime later, maybe t3, we measure the distance between those 2 points, and we can get the average velocity or flow of that fluid. So how do we find the equations of path lines? So again, we have our velocity vector. It has components u, v, and w. And so our path line equation would be if we integrate each of those components, u, v, and w, with respect to time. So if u, as we said before, is equal to dx dt, then we basically want to find a position x with respect to time of that particle. So we can rearrange it. X as a function of t is going to be equal to the integral of u dt. And then likewise, for our y component of velocity, dy dt, we can get an equation for y as a function of time, which is the integral of v dt. These are all integrals from 0 to t. And then lastly, w is equal to dz dt. So z as a function of time is equal to the integral from 0 to t of w dt. So then our path line is just would be our path line function. So after path lines, we have streak lines. Now, streak lines are probably the ones that we're the most familiar with visually because a lot of fluid flows, like the sprinkler, for example, tend to leave behind streak lines. So think of streak lines as if a source is leaving a constant stream of fluid or constant stream of particles, and we can see that constant stream as it changes through time. So I love the sprinkler example, and we can see that if we were to write an equation that would describe each of these lines of that fluid, just trace out a few of them, these would be our streak lines. So the streak line shows the path of many particles at the same time. And it's some snapshot in time. So to view a streak line, a stationary streak line isn't moving, and that would be at one instant in time. And streak lines will change with time if we have unsteady flow. All particles have the same origin in a streak line, and it's formed by a continuous introduction of dye or smoke or some unique fluid particles from a point in the flow. So now we have some definitions. Which of these pictures, what do we think that these are now? What is this top right one? Is this a streamline, path line, or streak line?
Streaks.
Yeah, that'd be streak lines. So in this case, they put ink on the car, and as they drive that car around, the airflow around is going to distort that ink, and the ink is going to flow down the side of the car, but the ink is all coming from one constant part. And then the bottom here, yeah, this could be streamline or path line. I'm not 100% sure. I think this is probably a streamline, maybe path line. So that one's a little bit more difficult to tell. It looks like some of the lines are crossing, so if it was streamlines, that wouldn't really be the case. This could be path line, could be streamline. So if we're confused as to which one is which, and we're thinking, I like to think of a streamline is a snapshot in time of velocity field. So if you draw the velocity vectors in the field and you take a snapshot in time, all those lines, those arrows, if you just draw lines through those arrows, that would be your streamline. A path line is a line that's traced by a particle. So give a particle a marker, Just let it draw on the wall as it passes by. That would be your path line. And then the streak line is the path connecting a steady stream of particles. So if you released a bunch of rubber duckies down the river one at a time, if you trace the line of all those rubber ducks from beginning to end, that would be your streak line. Is a streamline a photo of one particle? So a streamline is a photo of all particles in the fluid flow, but it's not necessarily a photo of the particles themselves. It's a photo of the velocity of the particles. So it is the velocity that determines where that streamline is. The path line and streak line are actually, we can visualize those as the particles themselves, but a streamline is a bit more abstract because it's not the particle, it's the velocity of the particle that we're seeing or visualizing. So there are a few methods in flow visualization that are used quite often, and there's more and more methods developed all the time to try and get better images, better ideas of what's going on in fluid flow. So one of the more common ones, and older style ones, would be to use dye or smoke or bubble discharges in a fluid. Another one would be use surface powder or flakes in liquid flows. So if you have little flakes of glass or something shiny or reflective submersed in or distributed inside of a liquid, and that liquid is flowing, and you shine a laser through that liquid, then at every point where the flow is reflecting that laser, you can get an image of the fluid flow, or you can track the fluid flow through time. You can have floating or neutral density particles that are moving along with the fluid, and you can track their motion to get a path line. There's optical techniques that detect density changes, so that would be like that Schlerin photograph we saw earlier. Another common one is to use tufts of yarn attached to boundary surfaces. This is quite common in cycling and the automotive industry, and there's also a picture here from NASA of using two of the techniques. One of them is using smoke injection to watch a streak line along the side of the fuselage, and then another one is to look at the flow along the surface of these fuselage and the wing, and that's using these little tufts, surface tufts, and they will just follow along in the direction of the flow. So they'll act more like streamlines in the flow, whereas the smoke acts like a streak line. We could put evaporative coatings on boundary surfaces or luminescent fluids, and that was like the Formula One car that we saw in the picture above. We could use particle image velocimetry or computational methods where we can simulate particles flowing over a body, or even new methods that we don't even know of yet. So let's do an example and then we'll take a break. So this is an example where we have a steady two-dimensional flow field. So let's point out it is steady and it's two-dimensional. So we have our x component of velocity is equal to u is equal to kx, some constant k times x. So our u component of our velocity is changing in the spatial direction x, and the y component of our velocity v is changing with our spatial y coordinate, and then our since it's two-dimensional, our z flow, the w velocity is just 0. So it says k is just some positive constant, and it's asking to compute and plot the streamlines of the flow, including directions, and give some possible interpretations of the pattern. So we want to find the streamlines of the flow. So we said in 2 dimensions, our streamline equation, if we go back up, be a little ways. In 2 dimensions, our streamline equation was dy dx is equal to v over u. So let's write that. And we know an equation for V is equal to negative ky, and u is equal to kx. So those k's would just cancel out, and we're left with negative y over x. So what we want to find for our streamline is in 2 dimensions, we want to find some function in terms of x and y. So we have dy dx is equal to y over x. So let's separate our y terms and our x terms, and then if we integrate, we should be able to solve for some function of x and y. So let's rewrite this. We can say dy over y. So make this side negative is equal to dx over x. If we integrate both sides, then we'll end up with ln x is equal to negative of ln y plus some integration constant we'll call ln c. And if we rewrite this and simplify, we could just write this as x times y is equal to c. So this becomes the equation of our streamline. So what does this look like? What does this look like when c is equal to 0? So if c is equal to 0, the product x times y is equal to 0. So yeah, one of x or y has to always be 0. So if x is 0, then y can be anything. And if y is 0, then x can be anything. So that line would literally follow the coordinate axes. So this would be c is equal to 0. Is it non-negative? I'm not sure what you mean by non-negative. C can be anything. It's just an integration constant. So this would represent at any specific point in our fluid flow, we might have, if we solve for this, we could solve for C. So say we knew a streamline or a point over here. The flow line that would go through this point might correspond to when C is equal to 3. So our flow might look like this. And then our direction of flow would be in this direction. So if we were to draw all of those lines for all of our different values of C, then we would have, for this case, our fluid is flowing in this direction. And then if C was equal to 1, we would have flow in this direction, in this direction. So this is C is equal to 1. This side is for C is equal to -1. This side is for C is equal to 1. And this is again C is equal to -1. So if we scroll down here, this is the work that we just did. And here's an actual full plot of what that streamline field would look like. So this streamline pattern is entirely independent of that constant k. It doesn't matter the magnitude of the velocities, it matters the relative velocities of x and y because that determines your direction. So how do we go from the ln stuff to xy? So let's remember the principle ln A plus ln B is equal to ln of AB. So if we move the ln y to this side, then we can say ln C is equal to ln xy. Take the exponent of both sides, the lns go away, and we're just left with C and xy. So we have C is equal to xy. So that's what our flow visualization would look like, our streamlined flow visualization. So if we wanted to describe what this could mean, if we see that all the flow is coming in at this end, make this more exciting. So our flow is entering at the top and exiting at the base. So maybe we could imagine this as, if we only considered the bottom, maybe this was a solid plate. It could be a fluid flow just hitting a flat plate. And the points where we would have zero velocity, so right here, v is equal to 0, this is what we would call a stagnation point. And we'll talk more about that later. So we'll leave it there, and we'll come back to our recap. I'll put it back on that slide. We'll just take a 10-minute break. So